Well, here we are again, Mrs. Hanson here, beginning with section 5.2, thinking about how to write a balanced chemical equation. We know that an equation depends upon having the correct formulas of both reactants on the left and products on the right. When we balance an equation, we use what are called coefficients to balance one element at a time. Remember the cardinal rule, never ever change a subscript in a formula to balance an equation. And finally, at the end, you want to make sure that your balanced equation is using the smallest sets of coefficients possible. Coefficients are always whole numbers, and they're in the lowest ratio possible. The best way is to just dive in and practice. Let's begin by writing out a balanced chemical equation from these words. Alrighty, so propane gas. Alright, so propane is given as C3H8, and I'll just add that little adjective G to let you know that the phase of matter of propane is in the gaseous form. Propane is that fuel you use in perhaps your gas grill at home when you light up to cook a burger on the grill. You're lighting propane. Here we see reacts with. That's going to be the plus sign, reacting with. Remember, oxygen from the air. Oxygen is one of the 7 diatomic molecules you need to memorize. Diatomic means oxygen never exists as just O, but it exists as a diatomic molecule. And I'll put little gas because I see it's from the air. The next words I read are to form, and that's the arrow. It's forming carbon dioxide gas. Then I see the word and, which is the plus sign. Water vapor. Water is H2O. The vapor is the little g for gas. I'm going to encourage you as you practice to give yourself space to let you remember where the coefficients go. Never put a coefficient in between a compound's formula. Always place it out front so it speaks to the entire compound. When we begin practicing, do you remember? This is known as a combustion pattern. We have a hydrocarbon fuel called propane, burning in the air with oxygen, forming carbon dioxide water, known as a combustion pattern. One of the 5 that we'll write down in our note packs. Let's create a T-chart to tally how many C's, then H's, then O's. And when you balance combustions, the best advice I can give you is get the carbons first, then the hydrogens, and save your oxygens for last. Let's count. On the left side, I can see a total of 3 carbons. I can see a total of 8 hydrogens. And I see a total of 2 oxygens. Individual atoms of carbon, H's and O, have been tallied. Do the same on the right side. I count 1 carbon, I count 2 hydrogens, and a combined total of 2 plus 1 more from the water is 3 oxygens. Remember that oxygen now is appearing in 2 separate places, so I have to combine the total to 3. Starting with your carbons, let's place in a coefficient and balance the carbons. I need a coefficient of 3 on the right-hand side to have 3 carbons. Fix your T-chart, because not only did you change the carbons, you also changed the oxygens. So no longer is there 3. There's 3 times 2, which is 6, plus 1 more yet over on the water. So that's a total of 7 oxygens. Carbons are good. Let's go down to the H's next. If there's 8 hydrogens on the left, let's place a coefficient of 4 in front of the water so that we can see 4 times 2 gives us 8 hydrogens. But fix your T-chart because you've also changed the number of oxygens. You have 3 times 2 is 6 from the carbon dioxide and 4 times 1 now, which is the number of oxygens in the water. So we have 6 plus 4 gives me a total of 10 oxygens. Now I can back up to the left side, placing a coefficient of 5. 5 times 2 gives me 10 oxygens. We know we're balanced by using the T-chart method, counting left and right. Our coefficient ratio reads 1 molecule of propane reacts with 5 molecules of oxygen to form 3 molecules of carbon dioxide and 4 molecules of water. Our balanced chemical equation. We can try another together. Write a balanced equation for the reaction of glucose. Glucose is blood sugar, C6H12O6. It's reacting with, so you hear that? That's a positive for, it's like an addition sign, glucose plus oxygen. To form is the arrow, and it's forming carbon dioxide and water. Now this pattern is getting very familiar, isn't it? You're recognizing it as a combustion pattern, taking a fuel such as a sugar, burning it in oxygen to release energy. The carbon dioxide that comes out, the water that comes out, and a whole lot of ATP energy if you know your biology. This looks like respiration. A beginning student does very well by practicing with these little lines in front to make you remember where the coefficients go to balance. We use a T-chart to balance. Do the C's, then H's, then O's. Tally up 6 carbons on the left, 12 hydrogens on the left, and 6 oxygens plus 2 more gives you 8 combined on the left side. All right, let's count 1 carbon, 2 hydrogens, and a combined total of 2 plus 1 more is 3 oxygens. Use your C's, then H's, then O's. Let's repair carbons first. Placing a 6 in front of the carbon dioxide also changes the oxygen, so make sure you see that. You have 6 times 2 is 12, plus 1 more in the water yet, so now we're at 13. Got the carbons working. Go down to your hydrogens. 12 on the left and only 2 on the right. So let's place a coefficient of 6 and repair your T-chart. 6 times 2 is 12 hydrogens. Now let's also take care of the oxygens. We still have 12 from the carbon dioxide. 6 times 2 is 12, but now we have 6 more from the water, giving us 18 oxygens. Now, with this example, we have 18 oxygens on the right side. We need a total combined volume, or total combined number to be 18. But remember, there's 6 of them already accounted for. So when I subtract 6, I really need 12 more. I don't want to put a coefficient here because I would change the carbons and the hydrogens, and I don't want to do that. I've got them all behaving. I don't want to put a coefficient there and mess them up. So I want to place a coefficient here that when added to the 6 oxygens present in the fuel, in that sugar, will give me a combined total of 18. 6 of them are already taken up from the sugar molecule, so we need 12 more. I can place a coefficient of a 6 right here so that I could get 6 times 2, that's 12 from the oxygen, plus the 6 from the fuel, and I have now 18. And that balances our equation. A 1 to 6 to 6 to 6, which is our respiration equation. And if you remember, if you reversed it, it would be called photosynthesis. The pattern of change is called a combustion. Now, this skill is a practiced skill. Practice, practice, practice. It is not taught to you by modeling, just, a few examples to give the idea. You have to really put the time in to get good at it. So here's your opportunity. Looking at page 3, you have an opportunity to just sit and practice balancing equations. Come on back to the video when ready to check your work. Pause right now, work to balance these, and then come back. All right, I really hope you took some good time to practice balancing. Letter A takes oxygen and hydrogen. And notice what I'm doing? I'm getting in the habit of showing that I want coefficients in the front of the reactants and products. Hydrogen plus oxygen combine to form water. We will learn that this is called a combination reaction, where things combine to produce a larger product. Combination has just one product. It's the opposite of a decomposition. T-chart, left, right. We want to count H's and O's. 2 H's, 2 O's on the left, 2 H's, 1 O on the right. So you repaired your oxygen by doubling the water. That got the oxygens working, but it also messed up the hydrogen. No worries, you backed up and you placed a 2 and repaired your T-chart. 2 to 1 to 2. 2 molecules of hydrogen react with 1 molecule of oxygen to form 2 molecules of water. Perfect. How'd you do for B? NO reacts with O2 to form NO2. This is also called a combination reaction. 2 or more ingredients combining to make a single product. That's how you'll recognize, when we get that far, you'll recognize a combination because it's the only pattern of chemical change that has just a single product. It is the opposite of decomposition. Let's tally our chart. We are counting N's and O's in letter B. We start with 1 nitrogen and 3 combined oxygens. On the right side, I have 1 nitrogen and 2 oxygens. So it's not yet balanced. The oxygens need to come up. Let's try a 2. We'll see what we get. That really didn't get me anywhere, did it? Because I can't turn a 3 into a 4. Now my trick for this, when it didn't work by using a 2, when it didn't work first, go to a 3. What I'm saying is, I put 2 in front of the NO2 and I couldn't get the oxygens to balance. So what if instead of a 2, I put a 3 there? Let's go back and just fix our T-chart. I had originally a 1 and a 2. When I put this down, I get 3 N's and 6 O's. All right, I like that because I can put a 3 here and get my N's to work. And 3 plus 2, oh, that's 5. There's 5 oxygens. You know, as I sit here and think, maybe you did this already, what was wrong with my 2? Because now I'm stumped. And yep, I am doing this on purpose, aren't I? If you notice that, I'm really challenging you by making mistakes and letting you think that out. When we started, we had a 1 and a 3. We had a 1 and a 2. And I placed a 2 here. And I had 2 N's and 4 O's. What's wrong with that? As I kind of go through, 2 N's, and 2 plus 2 is 4 O's. You got it. A 2 to 1 to 2 balance that equation. When I said a 2 didn't work, I went to try a 3. It didn't work. I went back to revisit my 2 and convinced myself, yep, that makes sense. I can get it to work. So I went and revisited. So my balanced equation is 2 to 1 to 2 for letter B. Okay, how about letter C? Let's see, we have a methane, CH4, reacting with chlorine to form CH2Cl2 and HCl. Did you create a T-chart? On the left and on the right, we have a carbon, a hydrogen, and a chlorine to tally. 1 carbon, 4 H's, and 2 Cl's. On the left side, let's see, I have 1 carbon, 1, 2, 3 H's, and 1, 2, 3 Cl's. Well, carbons look okay, don't they? So what do we want to do here? How about, shall we try to repair the H's by placing a 2 here and see what happens? I have 2 H's plus 2 more from here. That's 4. I like that. And we have 2 Cl's and 2 more. So that's good. And look what we could do. We can repair the chlorines to get a total of 4. 1 carbon on each side, check. 2 chlorine times 2, there's 4 Cl's on each side, perfect. And then of course the 4 hydrogens. So here we had a coefficient of 1 molecule of methane, 2 molecules of chlorine, made 1 molecule of dichloroethane, and 2 molecules of HCl. A 1 to 2 to 1 to 2. All right, let's keep practicing. So far when we get going, you might be able to find that you can just go back and forth in your mind and not really need a T-chart. But until you have that kind of proficiency, a T-chart is the way to go. Putting these in little lines help us remember where the coefficients go as well. So we have a left, right to keep track of. We have a nickel, a hydrogen, and a chlorine. We have 1 of each on the left side, 1 nickel, 2 hydrogens, and 2 Cl's on the right side. This one was easy. We doubled the HCl and have everything obeying the law of conservation of mass. A 1 to 2 to 1 to 1 balances that equation. We will learn that this represents a pattern of chemical change known as a single replacement. An element plus a compound, we will call it a single replacement reaction. An element plus a compound made a new element plus a new compound. We'll see that the nickel kicked out the hydrogen. There's the hydrogen all by itself and stole its partner, the chloride. A single replacement reaction. Letter B. We had methane, CH4, plus chlorine gas, Cl2, forming carbon tetrachloride, and HCl. Your T-charts, you had 1 carbon, 4 hydrogen, and 2 chlorine, 1 carbon, 4 chlorines, plus 1 more is 5, and just 1 hydrogen. Well, what about a 4 here right off the bat? Let's see what that does for us. And the reason I said that is carbons are good, so let's go down and repair the hydrogens. And by putting a 4 in front of HCl's, repaired the hydrogens. And what did it do now? What did it do now to the there we go, got it. There's 4 chlorines plus 4 more in the HCl. We have 8. Yep, 8 chlorines on the right side. Oh, easy peasy. We can put a 4 there and get 8. A 1 to 4 to 1 to 4 balanced that equation. 1 carbon, 4 hydrogens, and 8 chlorines on both sides of our arrow. Good work. Letter C, potassium chlorate. Oh, you did this in the lab. You took some potassium chlorate and you heated it to force it to decompose. Out came potassium chloride and oxygen gas. Now this is known as a decomposition reaction, a single product breaking down into smaller pieces, a decomp. When we do our tally, we have left and right. We're counting potassiums, chlorines, and oxygens. On the left side, there's 1 K, 1 Cl, and 3 O's. On the right side, the K's and the Cl's, but it's the oxygen that are not yet balanced. I'm going to turn this into an even number. And to do that, I'm going to double it. Let's double the KClO3. And I have to turn it into an even number because there's no way I can get an O2 molecule to ever come out odd, right? It only comes as even pairs. So when I double the left, I get 2 Ks, 2 Cls, and 6 Os. On the right, I can fix my KCls by placing a 2 in front of the KCl. Oh, we got it. Here's a 3, and I can turn that one into a 6. 2 KClO3s decompose to form 2 KCls and 3 O2s. There's your letter C. Letter D, Al2O3 plus HCl yields AlCl3 and water. Let's see, 2 aluminums, 4 guys to keep track of, 2 aluminums, 3 oxygens, 1 hydrogen, 1 chlorine, tallied the left. On the right side, 1 aluminum, 3 chlorines, 2 hydrogens, and 1 oxygen. All kinds of stuff to repair. For no other reason than it's written on the top, I'm going to start with aluminum. I'll do that by placing a 2 in front of aluminum chloride. Fix your T-chart. We have 2 aluminums, and now 2 times 3 is 6 chlorines. All right, that's fine. Let's see. Oxygens, there's 3 on the left. Shall we try a 3 on the right to repair the oxygens? There's 3 O's. Don't forget to repair your T-chart because now there's a total of 6 hydrogens as well. Oh, beautiful. How about a 6 right there? 6 H's, 6 Cl's. You got it. A 1 to 6 to 2 to 3 balances that equation. Do you recognize it? This is a double replacement. Aluminum went to chloride, hydrogen went to oxygen, a double replacement reaction. We'll learn that in the next section. Letter E, aluminum hydroxide plus sulfuric acid. Hydrogen sulfate is sulfuric acid, forms aluminum sulfate and water. You know what? I'm going to give myself a little more room for this one, and I'm going to show you a trick. I'm going to rewrite letter E down here where I have some space. This is what I want to do. I want to write aluminum hydroxide plus H2SO4 yields aluminum sulfate. And now for water, watch what I'm going to do. I'm going to write that as HOH. That's water, 2 H's and an O, but this is why I like to do it. Aluminum went to sulfate, hydrogen went to hydroxide. Notice now when I go to balance this equation, I have 4 characters. This is known as a double replacement reaction. The 2 positive ions exchange places. Aluminum sulfate, hydrogen hydroxide. Aluminum hydroxide, hydrogen sulfate. Notice the charges kept constant. We just exchanged partners, and now we need to balance. We have to count aluminum and hydroxides, hydrogens and sulfates. Leave those together. Remember that clues. Leave the polyatomic ions together. All right, now let's tally. On the left, there's 1 aluminum. There's 3 groups of OH. There's 2 hydrogens and 1 group of the polyatomic ion sulfate. On the right side, 2 aluminums, 3 groups of SO4. That's the 3 groups taking the unit SO4. There's 1 hydrogen, 1 hydroxide. Let's repair the aluminums first. I'll do so by placing a 2 on the left side. Let's repair the T-chart. Now I have 2 groups of Al, and 3 times 2, there's 6 groups of OH. All right, let's go down to the next character, the OH, hydroxide. We have 6 of them on the left. Let's put a 6 in front of our water. Repair your T-chart. Because now we have 6 OHs and 6 hydrogens. Count these separate. H, OH. 6 H's and 6 OHs. I really just want you to think of water as hydrogen hydroxide. When you're balancing in a double or even a single replacement reaction, this is so much easier than to separate out the O's and the H's. Aluminum's working. OHs are working. Let's get the hydrogens to work. So we have 6 on the right. Let's try a 3 right here. Repair your T-chart. 3 times 2 is 6 hydrogens and 3 groups of sulfate, 3 units of SO4, and we've balanced the equation. 2 to 3 to 1 to 6 balances letter E from our first problem. All right, good work. How about the second set? Magnesium plus HBr yields magnesium bromide and hydrogen gas. 1 mg, 1 mg, check. 1 H, 2 H's. I'll start by placing a 2 in front of the H and in front of the Br. And you know what we've done? We've balanced. When you look at your T-chart, the magnesiums, the H's, and the Brs. There's 1 magnesium. Perfect. There's 2 H's. Oh yeah. And 2 Brs. A 1 to 2 to 1 to 1 balanced. Here we have CO plus O2 going to CO2. 1 carbon on each side, perfect. 3 oxygens on the left, 2 on the right. Well, what we'll have to do is to kind of go like this. Let's try, what if we did a 2 and a 2? Repairing the carbons, there's still both 2 carbons. On both sides, and there's 4 oxygens on both sides. A 2 to 1 to 2 balanced your equation. Repetition. I hope you're still practicing. One PB, perfect. 1 S, perfect. 2 O's, 3 O's. All right, so that means we got to get this odd number fixed. 2 leads, 2 leads. 2 sulfurs, 4, 5, 6 oxygens, 6 oxygens. 2, 3, 2, 2. If that's too fast, slow down, stop the video, and count it for yourself. 2, 3, 2, 2 gave us 2 leads, 2 sulfurs, and 6 oxygens. H2SO4 plus NaOH yields Na2SO4 plus, here's my trick, water is HOH. Separate it out since it's separate over here. Do you recognize acid-base chemistry? H went to OH, calcium went to phosphate. So, whoops, same one down there, isn't it? Down here, sodium went to sulfate, hydrogen went to hydroxide. You're going to see that same pattern in a moment here. We're going to separate out HOH. So focusing in on letter D. Think of your T-chart now. You have 2 hydrogens and 1 sulfate reacting with 1 sodium, 1 hydroxide to form 2 sodiums and a sulfate and 1 hydrogen hydroxide. Hydrogen hydroxide, that's our water. All right, 2 NAs, let's double the NAs. 2 NAs, 2 NAs, perfect. 1 sulfate, perfect. 2 H's and 2 OH's means we doubled the water. Now, is that too fast? Are you getting so good you can do this with me? H, SO4, Na, OH. Those are the 4 characters we're balancing. On the left side, I count 2 hydrogens and 1 group of SO4. I count 2 NAs and 2 groups of OH. On the right, I count 2 NAs and 1 group of SO4. I have 2 hydrogens and 2 hydroxides combining to make 2 water molecules. So that's our T-chart for letter E. D, here's E. H3PO4 we'll learn as an acid, starts with an H, phosphoric acid. It's also reacting with a base, calcium hydroxide, CaOH taken twice. See how this is a double replacement? Calcium goes to phosphate. And remember, this is all based on charge. Hydrogen's a +1, phosphate's a -3, calcium's a +2, hydroxide a -1. So we're learning that these balanced formulas just come from crisscrossing charges. Hydrogen's a +1, hydroxide's a -1, so HOH. Same story up here, +1 -2, +1 -1, +1 -2, +1 -1. Those subscripts in the formulas are just simply there to balance electrical charge. I notice there's 3 calciums. That tells me to put a 3 in front of our CaOH taken twice. I see that there are now 6 hydroxides. 2 times 3 is 6 hydroxides. And then I can see that this will require a 2, Ca3PO4 taken twice, gives us 2 phosphates, 6 hydrogens, 3 calciums, and 6 hydroxides. 2, 3, 1, 6, checking your work for letter E. Oh my goodness, I feel so accomplished. We have just practiced balancing equations, and that took us very careful time. I mean, that was 30 minutes of practice. You included pausing your video and practice first. Now I'm going to stop the video here. We'll come back for section 2. Section 3, types of chemical reactions.